Hey everyone! This week we will go over lexicalized PCFGs, vector space models, and dimensionality reduction. So without further ado, let's get started. Before diving into the material, let's set the stage with today's learning objectives. First, you'll learn about lexicalized PCFGs, which extend the concepts of probabilistic grammars by incorporating specific words into the parsing rules. This will help us make parsing more precise and context-aware. Next, we'll cover vector space models, a technique for representing words as points in a continuous, multi-dimensional space. You'll see how these models capture semantic meaning and are integral to both NLU and NLG systems. Lastly, we'll explore dimensionality reduction, a key technique that allows us to simplify complex models while retaining the most relevant information. This is especially important when working with large-scale datasets like word embeddings or document vectors. Let's start with a quick recap of PCFGs, which you learned about in Week 7. A probabilistic context-free grammar adds a probabilistic element to traditional context-free grammars, CFGs, by assigning a probability to each rule. This allows us to handle syntactic ambiguity, the problem where a sentence can have multiple valid parses. For example, in the sentence, "I saw the man with the telescope," there are two possible interpretations. Either I used the telescope to see the man, or the man had the telescope. A PCFG helps the system choose the most likely interpretation based on probabilistic data. PCFGs are foundational in handling ambiguity, but they don't always give us enough precision, especially when the meaning of a sentence relies heavily on specific word choices. This is where lexicalized PCFGs come in, which we'll explore next. Next, let's talk about lexicalized PCFGs. A lexicalized PCFG takes the concept of a PCFG further by incorporating specific words, lexical items, into the grammar rules, rather than relying solely on high-level categories like noun phrases, NP, or verb phrases, VP. This allows the system to account for the relationships between specific words, making the parsing process more precise. For example, in a traditional PCFG, we might have a rule that says VP, V, NP, meaning a verb phrase can consist of a verb followed by a noun phrase. However, this rule is very general and doesn't tell us much about the specific words involved. In a lexicalized PCFG, the verb might be lexicalized, meaning that the parser knows the specific word eat is often followed by an edible noun phrase, like apple or sandwich. This added layer of information helps the system parse sentences more accurately, particularly in cases where word choice and word dependencies play a critical role in meaning. So what is another example? One of the key benefits of lexicalized PCFGs is how they handle word dependencies. When parsing a sentence, the system can now rely not just on general syntactic structures, but also on the specific words that appear. For example, consider the verb eat. Without lexicalization, the parser would treat eat as just another verb, which could be followed by any noun phrase, NP. But in reality, verbs like eat are often followed by nouns representing food, such as apple or sandwich. By incorporating these lexical dependencies into the grammar rules, lexicalized PCFGs can significantly improve the accuracy of sentence parsing. This is especially useful in more complex sentences, where knowing specific word relationships helps resolve ambiguities. Now let's look at a concrete example of how a lexicalized PCFG parses a sentence. In this example, we'll see how a lexicalized PCFG parses the sentence, "John ate the sandwich quickly." A traditional PCFG would break this sentence into general phrases like NP, John, VP, ate the sandwich quickly, and then further split the verb phrase. But with a lexicalized PCFG, the parser knows that ate is more likely to be followed by a specific noun like sandwich, a food item, rather than any generic noun phrase. The system also understands that quickly modifies the verb ate and not the noun sandwich. By adding lexical items to the rules, the parser becomes more precise and contextually aware, which is critical for handling more complex sentence structures where meaning heavily depends on specific word choices. This example highlights how lexicalized PCFGs refine the parsing process, making it more accurate than a non-lexicalized approach. Let's jump into section 2, where we will talk about vector space models and integrating NLU and NLG. Before we introduce vector space models, let's briefly recap natural language understanding, NLU, and natural language generation, NLG, two fundamental components in NLP systems that we first encountered in week 5. NLU refers to the process by which a system analyzes and comprehends the input it receives. For example, when you type a question into a search engine or speak to a virtual assistant, the system needs to understand what you're asking. NLG, on the other hand, is the process of generating meaningful and coherent text output based on that input. Think of it as the system's response. For example, a chatbot's ability to generate a relevant reply depends on its NLG capabilities. In today's lecture, we'll see how vector space models provide a framework for representing the meaning of words, sentences, and entire documents, which plays a crucial role in both NLU and NLG systems. A vector space model, VSM, is a mathematical model that represents words, phrases, or even entire documents as vectors in a multidimensional space. Each word is mapped to a point in this space, where words that are semantically similar, meaning they share similar meanings, are located near each other. This spatial representation of meaning allows systems to understand and process language in a way that is more fluid and intuitive than rule-based methods. The idea here is that by representing words as vectors, we can measure their similarity by looking at how close their vectors are in this multidimensional space. For example, words like king and queen will likely have vectors that are close to each other because they are semantically similar in many contexts. Conversely, words like king and banana will have vectors far apart because they share little to no semantic similarity. By leveraging these vector space models, systems can understand relationships between words at a much deeper level, supporting tasks like word similarity, document clustering, and even recommendation systems. What makes VSMs particularly powerful is that they go beyond exact matches of words. Instead of only understanding king as king, the system can generalize based on its proximity to related words like queen, ruler, or monarch, allowing it to understand text in a more nuanced, contextual way. This forms the backbone of many NLU tasks, like semantic search or question answering, as well as NLG, where the goal is to generate contextually appropriate responses. Next, let's jump into an example. Let's visualize how this works with a simple example. Imagine a 2D space where we plot the vectors for the words king, queen, man, and woman. In a vector space model, words like king and queen will be plotted close to each other because they share many semantic traits. They both refer to royalty, have a gender distinction, and represent people in positions of power. Similarly, man and woman are also close because they share semantic similarities related to gender. However, there's also a clear relationship between king and man, as well as queen and woman, indicating both gender and social roles. This 2D example is a simplified version of what's happening in real-world NLP tasks. In reality, these vectors exist in a much higher dimensional space, often hundreds of dimensions, but the core idea remains the same. Similar words are grouped together, allowing systems to recognize patterns of meaning even in more complex sentences. Next, in both NLU and NLG, vector space models play an important role in how systems handle language. In NLU, the system uses VSMs to understand the meaning of an input sentence. For instance, if a user says, "I need a hotel room," the system can map the word hotel to its vector and compare it to other vectors in its space. It might find that hotel is closely related to words like lodging, reservation, and stay, which can help the system understand the user's intent even if the exact phrasing is unfamiliar. On the NLG side, VSMs are useful for generating responses that make sense in context. Imagine a user asks, "Can you find a restaurant near my hotel?" By analyzing the vectors for restaurant, hotel, and near, the system can generate an appropriate response like, "Sure, here are some restaurants close to your hotel." The beauty of VSMs is that they allow NLP systems to flexibly handle the vast variability in human language, making them more effective at both understanding and generating natural-sounding text. Okay, let's now talk about some real-world examples. Let's look at how vector space models are applied in real-world chatbot systems. Consider the user input. I want to book a hotel. The chatbot first uses NLU to process this input by converting each word into its vector representation. The word hotel will have a vector close to related concepts like reservation, stay, and room. Based on these relationships, the chatbot understands the user's intent. Next, the system generates a response using NLG. By analyzing the vectors in its space, the chatbot can construct an appropriate reply like, I found a few hotels for you. Would you like to make a reservation? Here, the chatbot's ability to generate a relevant response hinges on its understanding of the semantic relationships between words, powered by VSMs. Finally, in Section 3, we will review dimensionality reduction. Now that we've covered how vector space models work, let's talk about a crucial technique that helps manage the complexity of these models: dimensionality reduction. In NLP, word vectors often have hundreds of dimensions, each representing a specific feature or context in which the word is used. While this high dimensionality allows for precise representations of meaning, it also introduces computational challenges. More dimensions mean more complexity, which can slow down models and make them harder to train. Dimensionality reduction techniques like principal component analysis, PCA, and t-SNE help solve this problem by reducing the number of dimensions in a dataset while preserving as much of the important information as possible. These techniques allow us to simplify the vector space without losing too much semantic accuracy. This not only makes our models more efficient, but also helps reduce the risk of overfitting, where the model becomes too specialized to the training data and performs poorly on new data. Okay, cool. Next, why is this important? High-dimensional spaces can be problematic in NLP due to what we call the curse of dimensionality. As the number of dimensions increases, the data becomes more sparse and harder to manage. This can lead to inefficiencies in both training and inference stages of a model. For instance, if you have a 300-dimensional vector for every word in a corpus, processing these vectors can become computationally expensive. This is where dimensionality reduction becomes essential. Techniques like PCA reduce the complexity of the data by focusing on the most important dimensions, those that capture the majority of the variance in the dataset. At the same time, less relevant or noisy dimensions are discarded. This simplification makes models run faster and helps ensure that they generalize better to unseen data. It's especially critical in large-scale systems like Google Search or recommendation systems, where the speed and efficiency of vector computations directly impact performance. Great. Let's take a look at an example of dimensionality reduction using PCA. Imagine we have a high-dimensional vector space representing words like king, queen, man, and woman. Each of these words might originally be represented in a 300-dimensional space, where each dimension captures some aspect of the word's meaning. Applying PCA, we can reduce this down to just 2 dimensions, while preserving the relationships between these words. In this reduced 2D space, we'll see that king and queen remain close together, as do man and woman. The reduction process keeps the most important relationships intact, but simplifies the vector space, making it easier to work with. This is particularly useful when processing large-scale data sets or when visualizing complex word relationships. What's a real-world case? Dimensionality reduction is widely used in real-world applications where processing large amounts of data quickly is essential. Take Google Search as an example. When you search for a phrase, Google's algorithms need to compare your input against billions of documents in real time. By applying dimensionality reduction to its vector space models, Google can reduce the complexity of this task while preserving the semantic relationships between words and documents. Another example is in recommendation systems, like those used by Netflix or Amazon. These systems analyze user preferences and product features, often represented as vectors, to generate recommendations. By reducing the dimensionality of these vectors, the system can make faster and more accurate predictions without losing critical information about user preferences or product features. Let's look at a real-world example of dimensionality reduction in action: Netflix and its recommendation system. Netflix collects an enormous amount of data about users' preferences, what shows they watch, their ratings, and how long they watch each program. This data is represented in high-dimensional space, where each user might have hundreds or thousands of features associated with their preferences. However, using all of these dimensions can slow down the recommendation process and even lead to overfitting, where the model becomes too focused on specific data points. To solve this, Netflix uses principal component analysis, PCA, to reduce the dimensionality of these preference vectors. By doing so, they can capture the most relevant patterns, like general preferences for genres or actors, while discarding the noise, such as highly specific and less useful features. This reduction allows Netflix to process data more efficiently and generate personalized movie recommendations more quickly. The recommendation system becomes faster and, importantly, more accurate because it can focus on the most important features of user behavior without being overwhelmed by too many irrelevant data points. This same approach is used in many other recommendation systems, from Amazon's product suggestions to Spotify's playlist recommendations. This has been great. If you have any questions or concerns, feel free to reach out. Thank you.